clustering is essentially organizing the data into clusters, okay, or into segments or groups, such that within the cluster there is a lot of intra-cluster similarity. Okay, so if I place multiple data points into one cluster, the similarity between those 2 points is very, very high. Okay, that means they are very close to each other, and therefore they are put into the same segment or same cluster. Like if purchasing behavior of two of my customers are very similar, then I will put both of them into the same market segment. Okay, so there is a high intra-cluster similarity. Okay, at the same time, there is a low inter-cluster similarity. Okay, if I have customers from 2 different segments, their purchasing behavior should be as different as possible, right? If that is also same, then there's no point in putting both of them in different clusters or different segments, right? So the goal of clustering is to organize data into clusters such that there's a high intra-cluster similarity, that means within the cluster, and then there's a low inter-cluster similarity, that means between the clusters. Okay, and we need to find groupings or clustering in order to account for those restrictions of high intra-cluster and low inter-cluster. Okay, the third point is simply finding the natural groupings among objects. Okay, like for example, if I have data points like this, okay, if this is my data, a bunch of points, a natural grouping is obviously this is one cluster and this is one cluster, right? Because they are kind of close to each other. So that's why it's kind of informally, that's what you're trying to do. You're trying to find the groupings that you normally do just by looking at them. Okay, does that make sense? Good. Okay, let's go. So Ashish says, can you please tell what is a typical problem statement in clustering? Identify into clusters or further optimization. So the problem statement can be just to find market segments in my customer base. That itself can be a problem statement. Or it can be something else for which you find clusters and then build on top of that. Okay, like in order to answer that, let me give you another example. In any store like Walmart or Macy's or any store, you have a lot of promotions, right? Sales. Now, how do they figure out which item to put on sale? And even if they determine this item should go on sale, what is the percentage discount that they should give? Okay, and typically they give something like in the first week of promotion period they give you 10% discount, and after a week they give you 20% discount, and after 2 weeks they give you 30% discount, just to make that item go away from their shelves. Okay, so and typically you can't do this kind of analysis, meaning figuring out that particular schedule, right? Like first 1 week should be 10%, second 1 week should be 20%, and so on. So that's kind of called as a schedule or a markdown schedule. Okay, figuring out that particular schedule for every item in your store is impractical and may not be useful also. Like Walmart has millions of items or thousands of items, so you can't come up with that schedule for every single item. Okay, so typically what they do is they kind of categorize all your products into different categories, and then analyze individual categories one by one. Okay, so that's kind of making your problem of finding the markdown schedules for all your products little easier by finding out some clusters within your product portfolio. Okay, and the clusters can be like all the items that have similar sales profile will go into one cluster, or all the items that that are targeted at a particular set of customers will go into one cluster. That can be whatever the store manager decides, but essentially you are dividing your products into different clusters and then trying to figure out a markdown schedule for individual clusters. Okay, so here the end goal is to figure out the markdown schedules, but you are relying on the clusters in order to get to that that thing. Okay, so the problem scenario, the problem statement need not always be saying, okay, find the groupings. Okay, it can be something else, but you start with the groupings and then build on top of it. Does it make sense, Ashish? Okay. And yeah, so we already talked about a bunch of things here. Why clustering? Organizing data into clusters to show the internal structure that is present in the data, or the internal groups. Okay, and sometimes, as we just discussed, partitioning itself is a goal, like finding the segments in your customer base, or prepare for some other machine learning techniques like summarizing the news, or in this case finding out the markdown schedules. And discovery in data is simply just to understand the data. Okay, just to see how the data is there, like as an exploration. You can use clustering as well. Okay, and there are multiple types of clustering algorithms, not just multiple techniques of solving a clustering problem, but there's also multiple types of what clustering is, or what the goal of clustering is. So one is exclusive clustering. That means it's like a partitioning. You're dividing all your data points into partitions so that every data point belongs to a single cluster or single partition. Okay, there's no overlap. Whereas in the other case, this one, overlapping clustering, a single data point can belong to multiple clusters. Okay, so it's not really partitioning in a hard manner, but you are allowing for these multi-membership cluster. Okay, so typically this is called as a hard clustering. So you're partitioning so that one data point belongs to one cluster. And the overlapping clustering is also called as fuzzy clustering or a soft clustering. Okay, where you can have multi-membership. And this can also be useful depending on the application. Like if I want to, one popular example is if I have all the users of Twitter and I want to group them based on their interests. Okay, then one person can be interested both in sports as well as politics. So that person should belong to both the sports cluster as well as politics cluster. Okay, so there the multi-membership kind of makes sense. Okay, and there may be other applications where exclusive clustering makes more sense than overlapping clustering. Okay, so depending on the application, you figure out which one to use. Okay, and there's also something called as hierarchical clustering, which is typically done in a, obviously as the name suggests, it's done in a hierarchical manner. Okay, so actually let me take one example, and that should give you better understanding. One classic example for that is something called as a phylogenetic tree. Okay, something like this, which is like an evolutionary tree. Okay, this evolutionary tree essentially connects all the organisms in the world, in the planet, and trying to, so it's like we always hear that humans and chimpanzees are close to each other, right? They're kind of coming from the same ancestor. And if you like draw this entire evolutionary diagram, even humans are similar to frogs, or humans are related to dinosaurs and so many other organisms in certain manner, right? So the way that evolutionary tree looks like is something called as hierarchical clustering. So here in this particular example, in this particular picture, we are grouping all the dinosaurs, different species of dinosaurs, right? So imagine this tree to be upside down, just to understand even in a nicer way. At one level, you are kind of combining these three into one grouping, okay? And then you are connecting that group with other species. Then you get this group. And then you combine this group with other species, you get this group. So you are going step by step in constructing these groupings, okay? And that's why it's called hierarchical. And at any point, you can kind of draw your line and say, okay, these are the groups I can look for, these are the things that I want to focus on, and so on, okay? And typically, when you do hierarchical clustering, you construct something called as a dendrogram, which looks like this. So at lowest level, every one of your data point is an individual cluster, and then you hierarchically kind of merge individual data points to become a cluster, and then that cluster is merged with some other data point to become another cluster, and so on. And you keep going up and up and up by grouping more and more data points, okay? Since you go in this hierarchical manner, it's called hierarchical clustering, okay? So as you can see, this is different from the partitions that we constructed, something like here, right? Here we simply say all of these data points belong to one cluster, all of these data points belong to one cluster. There's no hierarchy here, whereas here there's a hierarchy. And depending on the application, this may be more useful than this kind of partitioning kind of approach, okay? All this particular slide says there's no one answer to any clustering. There can be multiple arrangements of the data that kind of satisfies your requirements or constraints. So it really depends on whether a particular solution is sufficient for you or not, okay? And okay, so in this slide, we said clustering is something where you organize your data points into clusters or groups or segments such that there's a high intra-cluster similarity and low inter-cluster similarity, right? We are okay with that definition. However, the subtle point is that the notion of similarity, okay? In order to say there is high intra-cluster similarity, first I need to define what is similarity, right? I need to, for a bunch of data points, I need to define a similarity metric that is applicable over those data points. And depending on the data, the type of the similarity measure or the type of the distance measure, which is the opposite of similarity, can change, okay? And in order to do, before we execute any clustering algorithm, the first and foremost thing that we agree upon is the distance measure or the similarity measure that needs to be used, okay? And there are many formulations of distance measure or the similarity measure, okay? And depending on the application, you use one over the other. And in a lot of cases, you don't even know what to use, so you just try a bunch of things and see which one kind of gives you nice results. Okay, and as we just said, similarity and the distance are kind of opposite to each other, right? Distance, or also called as dissimilarity, are kind of two faces of the same coin. Okay, and for any clustering algorithm, you either need a similarity measure or a dissimilarity measure, one or the other. And these measures reflects the degree of closeness or separation between data points. Okay, that's clear, right, to everyone? Like in our market segmentation example, in order to say the two customers have the same or a similar purchase behavior, I need to mathematically quantify that similarity between their purchase profiles, right? And that's exactly what this notion of similarity measurement. Is that clear to everyone? Once we have such a notion, then we can obviously say whether the clustering mechanism method has high intracluster and low intercluster and so on. Okay, and as we just said, similarity measures. Similarity measures the degree to which a pair of objects are alike or similar. Okay, and yeah, so essentially says similarity as matching, according to which patterns are seen as different viewpoints, possible instantiations are. So yeah, you can go through the slide, but all it says is there are multiple types of similarity depending on the underlying data. Okay, and there are well-known distance measures that are typically used in many applications, but you can devise your own distance measure for your data set. That's totally possible, and many people do that because only you know more about the data, and therefore only you know how to capture the similarity or the dissimilarity between two data points. Okay. And the popular distance measures are, one is the Euclidean distance, which is the most popular, and probably all of us know it already, which we learned in high school. Euclidean distance between two data points in the space. And there's something called Manhattan distance. We'll see what that is. And there's also cosine similarity or cosine distance, Tanimoto distance, squared Euclidean distance, and so on. Okay. There are many more, not just these, but these are like popular names that you will see in practice. And Euclidean distance is simply the distance or the length of the line that is connecting the 2 points in the space, right? If I have the points 2, 2 and 6, 6, the Euclidean distance between them is simply the length of this particular line that connects this point and this point, right? And the way you compute that length is by applying this formula, okay? You essentially take the difference between individual components and then square it, sum it, and then take a square root. Okay, so essentially the distance between these 2 points is 6 minus 2 square plus 6 minus 2 square and square root of the whole thing. Okay, that's the Euclidean distance that we already know from our school days, right? And in practice, so in this example, your data is only 2-dimensional. So you have x and y coordinate, okay? But in general, the data can have many dimensions, right? And therefore, each data point is represented by n-dimensional vector or a coordinate format. Okay, so here A1, A2, A3, An are n different dimensions of the same point. And in this example, n is equal to 2, and A1, A2 are 2 and 2. And B1, B2 are 6 and 6. Okay, so that's the way you represent your data points in an n-dimensional space. And n dimension means n different features that are present in your data. Okay, like if I want to represent my customer as amount of money that he spends in my store per every week, and the age of the customer, and the gender of the customer. Okay, if I have these three data attributes that I want to capture, then my n is equal to 3. Okay, because every data point that I collect will have these three values associated with them. Okay, so yeah, if I have n-dimensional data points, then my Euclidean distance is this, and the Manhattan distance is computed like this. Okay, it's simply the absolute difference between individual components, like A1 minus B1, take the absolute value, and then you sum those absolute differences. Okay, and what you get is something called as a block distance. So Manhattan distance is also called as block distance. And if you are in US, or if you are familiar with what Manhattan is, the roads in Manhattan are strictly organized, or mostly organized into these squares, right, into blocks. And essentially, if you are in at a building here and you want to go to a building here, the route that you will follow is essentially different blocks that you traverse, right? You go from here to the next intersection, and from there you go to the another intersection, and then keep going. Okay, so this is like Chandigarh in India, which is the only planned city that we have, where all the roads are organized in a nice block structured manner. And what you get out of this particular equation is the number of blocks that you traverse in order to go from one point to the other point. And that's why it's called block distance as well as Manhattan distance. Okay, and in certain applications, or for certain data, this Manhattan distance makes more sense than computing a Euclidean distance. So that totally depends on the application and the data. Okay, so there's no like a silver bullet or one size fits all kind of a distance. It really depends on what you're trying to do, what is the data, and what is the application. Okay, any questions so far? And in practice, if you don't know what to do, you just simply apply Euclidean and see what you get. Okay. Okay. So this is another distance or similarity measure, cosine distance or cosine similarity, which kind of measures the angle between the 2 points. So here the 2 points are A and B, x1, x2, or A1, A2, B1, B2 instead of x2, y2. And the distance, the cosine distance, is essentially driven by the angle between the two vectors. Okay, and so tomorrow or end of today, we will see this document clustering example, which is like the Google News that we talked about. In those scenarios, you will use cosine distance. Okay, the angle between them. And Srinivas says, how do you know what you got is correct? So I just mentioned that if you don't know anything, you try bunch of measures and see the performance, right? And how do you know one is doing better than the other? That you typically do, that you typically evaluate by looking at the resulting clusters. So probably you can eyeball, I mean, if you can, you get some sample of data from each cluster and try to make sense whether those data points really should go into the same cluster or not. Okay, because for any application, you already have some kind of idea how those clusters should look like, right? If it's a sales profile, if I'm doing market segmentation, then I know that, like for example, for a distance measure like cosine distance, if I apply it on my market segmentation data, and if in the resulting cluster, person who spends only on necessity items and the person who spends on high-end computer games, if both of them are put into the same cluster, then I try to question the result, right? So those are the things that you can kind of eyeball the data and figure it out. Or there are, as we'll see later on, there are certain quantitative measures that you can compute, and based on those measures, you can evaluate one cluster is better than the other cluster. Okay? And so these are common things, but you will also have similar equations for Tanimoto distance and many other distances as well. Like if you have string data, for example, you will not use something like these measures, but you will use something called as a Hamming distance or a edit distance. Depends on the data, your distance measure will also change. Okay? So now that you have these distance measure defined on your data, our next goal is to actually go ahead and do the grouping or clustering, right? Look at the data points. You already have the distance or similarity measure defined on those data points. Now your goal is to find the groupings, okay? And as we already said, the goal is to have a clustering arrangement such that you have high intra-cluster similarity. That means within the cluster, the points should be close to each other in terms of the distance measure or the similarity measure that we just defined. And between the clusters, the similarity should be as low as possible. Or in other words, within the cluster, the distance should be small, and across the clusters, the distance should be large. Okay? Now, this is our goal, and let's see how do we get to that goal. Okay? And one algorithm that we'll see in this context is something called as k-means, which is the most popular one. And without this, you can think as you don't know what clustering is. Okay? So this is a fundamental technique. And this is example of clusters, which we already talked about in, we have seen many other examples. Like here, my data has only two dimensions. One is gross monthly income, and the other one is current balance of that particular customer. Okay? And I have many data points. And clearly there are, in this particular example, let's say there's one cluster here, one cluster here. Okay, and by looking at those clusters, I can kind of make some conclusions about those consumers. Like for example, this cluster, people in this particular cluster have high balance but low income. Okay, so that tells you something about their financial situation. Okay, and similarly, these are the guys who have high income and low balance. That means they keep spending a lot. Okay, and if you have, let's say, a new product for credit cards, depending on the semantics that you will derive from these clusters, you may be trying to target that particular credit card product to this cluster over this cluster. And similarly, if I have a loan product or some other product, I may be targeting this particular segment than this particular segment. Okay, that's a subsequent thing that you can do on top of this clustering. Okay, but the thing is that all the people in this particular cluster, the distance between them is very, very small. Okay, all of them have high balance and low income. And if I take 1 point from here, 1 point from here, the distance between them is typically large. Okay, and that's why they are put into two different clusters. Okay, and that's why there will be much differences between objects from cluster 1 and objects from cluster 2. Okay, and Gaurav says, what are the other clustering techniques? Which ones to use when? So after we discuss k-means, I'll show you other popular clustering algorithm, at least the names, and so that answers your first question of what are the other clustering techniques. We'll see what they are later. And to your second question, which is which one to use when, that's again there's no clear answer to it. Again, there's no silver bullet, there's no one size fits all kind of a clustering technique. It always depends on the data and what you're trying to do. Okay, so yeah, there's no clear answer for it, and you will see this kind of question coming again and again for every class. Like when we look at classification algorithms as well, there are like 10 different classification methods that are available. Which one to apply when? Again, nobody knows. There's no clear answer. So you typically just try a bunch of algorithms and see which one gives you better performance. Again, that better performance, you can either quantify it or kind of see what those results are by eyeballing it. Okay, and Sudhir says, what are the features you use to get these clusters? So features are exactly the dimensions, and in this particular example there are two dimensions or two features, which are the gross monthly income and current balance of the customers. So if you imagine the data, input data, it's essentially like a 2-column data where each row indicates a customer, and the first column indicates current balance, second column indicates gross monthly income. Okay, so in other words, I mean, just for the purpose of others as well, I'm using these terms interchangeably. Dimensions, features, or variables, or columns, all of them refer to these different attributes with which we are going to learn. Okay, and that's why in this particular case there are two dimensions, or two variables, or two features. Okay, all of them are the same thing. Make sense? Okay. So this is the algorithm that we are going to use in order to compute our clusters using k-means. Okay, and at the end of this slide you will realize why it's called k-means. Okay, and the first thing to understand here is the k. K is the number of clusters that you want to compute from the data. Okay, so this is an input to the algorithm. It's not something that algorithm finds, but it's something that you as a user should give it to the algorithm. Okay, so you will give two things to the algorithm. One is the data, actually three things. One is the data, other one is the distance measure. How do I compute this distance between the two data points? And the third one is the number of clusters that you want to compute. Okay, so given these three things, the algorithm will go ahead and find those many clusters from the data. Okay, and how does it find? Let's go through this flowchart and we'll understand what that is. Okay, so we have the number of clusters k, which is the input to the algorithm. The first thing that you do is select random k cluster centers. Okay, meaning randomly select k data points. Okay, and then so essentially, I mean, going back to this diagram, so I have data set like that, right? Bunch of points in the space. Okay, and I'm saying, let's say k is equal to 2. So I have all this data in a flat file, like a CSV file with XY coordinates, and I'm saying, okay, take this data, use Euclidean distance as the distance measure and take k equal to 2 and give me the two clusters that are present in this particular data. Okay. So what we are going to do, first thing is I randomly choose, okay, let me change the color of my pen. So I am going to randomly choose k data points in my data, k points in the space, okay, which can be, let's say, here is one point and here is another point, okay, randomly. And I'm going to organize my clusters around these red points, which are called as cluster centers, okay. So also called as centroids, okay. Now once I select these two red points, I'm going to compute the distance between every point, every data point, and the centroid that we chose. So I compute the distance between this black point and the two red points. And then I'll take another data point here, and I compute the distance between the both red points. And similarly, I take this data point and compute the distance between that and this point, and this data point and this red point. Okay. So I compute the distance between my data objects and the centroids. Okay. Now, what do I do with these distances? I essentially use these distances to assign my individual data points to the best cluster centroid that I can come up with. Okay. So that means I have, let me change my color again. I have this data point, okay, and I compute two distances between this one and the red point, this one and this red point. So I have distance d1 and I have distance d2, okay. Sorry for my bad writing, but I hope you can understand. So I compute two distances, d1, d2, and I choose whatever is the lowest one, okay. So let's say d1 is smaller than d2, then I'll say this particular data point belongs to this particular cluster center. That makes sense, right? Because I'm assigning my data point to a cluster center which is closest to that data point, okay. And that's exactly what's done here. So you're grouping these data points based on the minimum distance. So you do that for this one black point, and you do the same thing for other black point, and you do the same thing for all the black points, okay. You're essentially computing the distance between my black points, which are your data points, distance between those data points and your cluster centers, and then you're assigning to the cluster center which has the closest distance, okay, or the smallest distance. So at the end of that, essentially I have for this red point, I have bunch of points associated with them, right? And similarly for this data point, I have another bunch of data points assigned to that, okay? So that kind of gives you one version of grouping, right? That's essentially what you're constructing. You're essentially randomly chose two red points, and then you're assigning all your black points to one of these red points, okay? And at the end of this, you get something like that, some clustering of your data points, which may be bad, but that is what you have at the first at the end of the first round, okay? Any questions so far? So Sajjad, are you okay with it, or? Okay, Dilip says, what happens if distance d1 and d2 are equal to both centroids? Then in that case, I'll randomly assign it to one of them. It doesn't matter. Okay, Srinivas says, what if the data point sizes are different? What do you mean data point sizes? Yes, I can unmute you. Go ahead, Srinivas.
Yes, when I meant data sizes, right? So for example, if you go back to your slide again, so in this case, let's assume you had 20 of them in the top one and then 40 of them in the second one.
That's fine. Doesn't matter.
So
we are essentially saying if I divide my data into clusters and one cluster is smaller and another cluster is larger, that's totally fine. Because there's no requirement in our problem statement which says the clusters have to be equal size, right? The only constraints that we have is within the cluster, the similarity should be high. Across the clusters, the similarity should be low. Those are the only constraints that we have.
Okay, then how can you balance this out? I mean,
okay, that's a different constraint that you're trying to bring in, right? The balance between the clusters. Why should I mean, balance need not be important for all the applications, right? Like for market segmentation, for example. What is the use of having balanced clusters? I can have one high-end customers who spends a lot, which may be very, very small compared to a segment which spends on necessity items, right? So one cluster is small and the other cluster is large. That's totally fine with me, right?
Okay.
You don't sound convinced.
I'm not able to relate it to some. It'll take some time, I guess, but I'm still getting into.
But in this example, do you see the requirement of having equal cluster sizes?
Probably not. Probably not. I mean, I'm still trying to correlate to the real application where I can apply things and then start this one. But I'll get there. No worries.
I mean, just hold on to that, and maybe it will clear once we go a little further.
Yeah.
Okay.
All right. Thanks.
And okay, bunch of other questions. Let me. So Vivek says, how do I choose a centroid? We'll get there, but for now, just assume that these are two randomly chosen red points. Okay. And this is only the first iteration. We are going to do that again and again in order to get better cluster centers. We'll get there in a minute. And Anurag says, don't you think algorithm should automatically mention that how many clusters should be good? Okay, that's again another question. I'll get to that. No, Sudhir says we can use the same low balance and high. Oh, yeah. So he's just saying that in this particular example, which is good, Sudhir. So in this example, the number of people in this particular cluster may be totally different from the number of people here, right? There may be very few people with high income and low balance, but there may be a lot of people, depending on if it's a developing country, then there'll be a lot of people in this particular cluster than this cluster, right? So this is one example where the cluster sizes can be different. There need not be a balance between them in terms of the size. Okay? I hope that helps a little bit to you, Srinivas. Okay? Ashish also asked about what is the value of k. We'll get to that. Hold on to that question. Okay? So what we have done so far, given a k, we came up with one possible clustering arrangement around these randomly chosen red points. Okay? But this is not the end of the clustering. What we do next is so once you draw this green line based on the distances that we computed, we take the average of all the data points that are belonging to one cluster. Okay? So you are trying to move your red point to a better location. So essentially what we are saying is once you assign all these data points to a red point that we have chosen randomly in the initial phase, once I get this green circle, I am going to compute the average of all these data points. Okay, and then that average will obviously be somewhere kind of in the middle of all this, right? Let's say that average is here. Okay, so my cluster center has moved from here to here. Okay, and similarly I compute the average of all these data points, and then I'll get a cluster center here. Okay, so now we have two new cluster centers. So I go back again. These are the new cluster centers I have, and then I repeat my process. Okay, that means given these two red points, I compute the distance between the black point and the red points and then assign it to the closest one. Okay, so I keep repeating this until certain criteria is met. Okay, we'll see what that criteria is, and we'll see better example. Probably that will help you. Let me just go to other slide because this slide doesn't have colors. So okay, imagine this is your data points. The figure 1 is your data points. Okay, and the colors of the points are given just for your understanding purposes, but initially everything is a black data point. Okay, so these are a bunch of data points that are in the space and you want to cluster them. And I randomly chose k data points, k stars. Okay, these are the k centers that I randomly chose. And the first thing I do is compute the distance of every data point with all the k centers and then assign it to the closest center. Okay, and in this particular arrangement, all these data points happen to be closer to green star, so they are given green, and then all these data points closer to the red star, so they are given red color, which is to say that these data points belongs to this particular cluster center. And then similarly for these data points, the brown one was the closest, so I gave brown color, and similarly pink. Okay, so this is like the end of our first iteration. I start with the all black points. I compute 4 distances for every data point, which is distances to pink star, brown star, red star, and the green star. And then I choose the smallest. If the smallest is a green star, then I give a green color. If the smallest is red, then it's red color, and so on. Okay, so essentially all I'm saying is I'm assigning my data point to the closest center that I have. Okay, now once I do all that, I'll do the mean computation. So I'll take the mean of all the green points. Okay, then obviously my mean will be somewhere in the middle of all these data points, so it's here. Okay, so my green cluster center has moved from this range, this area, to this area. And similarly I compute the mean of all the red points, so my cluster center became this one. And then I compute the mean of all the brown points, so the cluster center became here. And similarly compute the mean of all the pink points, my cluster center became here. Okay, so after the first iteration, my randomly chosen stars have moved to some other location based on the data that I have in the analysis. Okay, now I repeat the same thing again. For every data point, I compute 4 distances again with pink star, brown star, red star, and green star, and then I assign it to the closest one and then give that color. So for these data points, green is the closest, so I gave green color, and similarly for red data points I gave red color, and so on. Okay, and then once I do that assignment, I do the average again. So then my stars will move to certain other location. So in this case, pink moved here, brown moved pretty much the same, red also moved very little, and the green moved little. Okay, and then I keep repeating, and at some point I will basically, in this particular example, we converge to something like this. So all of this is red, all of this is green, and this is brown, this is pink. So these are the 4 clusters that I have. Okay. So Srinivas, why do you think the data points have moved? Data points are exactly the same. We are simply moving the cluster, moving the stars, as well as the assignment of data points to the stars. That's what is moving. So if you just think about it, all we are doing is we are starting randomly 4 stars, and then we are moving those 4 stars according to the data that we have. So ultimately, the stars kind of went to the centers of different clusters. Okay? And the practical examples are like we just saw, right? This is one practical example. So here the data points are 2-dimensional data points, and if you do that kind of computation, you essentially come up with these clusters, which are kind of close to each other in the space.